Hey guys, today we are going to go over limits approaching infinity. So we'll talk about what happens as different functions grow infinitely large, grow towards negative infinity, or grow infinitely small towards zero. So the first activity that we usually do when talking about this is we compare different types of functions. So we're going to be looking at exponential functions, polynomial functions, trig functions, specifically sine and cosine, and then logarithmic functions, and see which function families usually end up always winning as x approaches infinity. And by winning, we mean which ones get larger faster. And so to save a little bit of time, I've gone ahead and I have graphed each pair of functions. And so then we're just going to go through and make sure that we understand which ones tend to dominate other functions. So this first graph is an example, or your exponential function is the red one, and then your polynomial function is the blue one. So obviously, as x goes to infinity, so as I go this way on my graph, my exponential function grows much faster than my polynomial function. So over here, we would go ahead and we could circle our exponential function. All right, if we look at the graphs of the next two, so my sine function is the oscillating one, the red function, and my logarithmic function is blue. And so even though my logarithmic function doesn't grow very quickly, it still is going to increase and get larger faster than my sine function. My sine function actually is always going to oscillate for all time. So we'd say the logarithmic one wins here. Between my next two, I have an x squared plus 7 function, which is this parabola, this red parabola, and then my sine function down here is again oscillating. So between my sine function and my polynomial function will also grow larger, faster. In the next pair, I have, in the next pair, I have an exponential function, this red one, and then a logarithmic function, which is the blue one down here. And so obviously my exponential grows faster. In this one, I have another example. I have a logarithmic function, which is the blue one, and then I have a polynomial, which is the x to the 2.5. And so my polynomial function actually beats out my logarithmic function because it gets larger faster. And then last but not least, we're going to compare an exponential function and a trig function. So hopefully you kind of understood, but this trig function, again, sine or cosines always oscillate, and my exponential function will grow larger much faster. And so what we'll do is we'll use this to kind of determine like what functions always grow larger, faster, and then which functions never win, kind of. So looking at these examples, we can see that, for example, your sine and cosine functions never won. So trig functions tend to be the least dominant of all your equations, whereas your logarithmic functions sometimes win, but it looks like logarithmic functions only win against trig functions. So those might be the second least dominant. And then between your polynomial and exponential functions, the exponential functions won every single time that they were paired against anything. So we would say the exponential functions are the most dominant, and we'll kind of put this into more formal note taking in a minute. Next, just to kind of clarify what it means to approach infinity. So it's the eventual end behavior of a function. For x approaching negative infinity, we consider the left side of the graph, so what happens as you go to the left. And then for x approaching positive infinity, we consider the right side of the graph. And then now we have looked at a little bit of function dominance. So the functions that dominate others means that they will end up growing or shrinking faster and therefore outpace other functions. So that means that no matter what is happening at a particular x value, as x goes to a negative infinity or infinity, some functions will just win out and outpace every other function. And this is kind of the formal note-taking version of what we talked about in our Desmos activity. So exponential functions are the most dominant, and amongst exponential functions, larger bases are greater than smaller bases. So larger bases, like if you had 12 to the x, that's going to beat out, like that'll be greater than 3 to the x. Okay, And so the largest exponential base that you can find, that's going to be the function that determines a lot of what happens as x approaches infinity and negative infinity. Next highest, or the next most dominant, are polynomial functions. So larger exponents versus smaller exponents. Larger exponents will win. So if you have, for example, x to the 24th, that's going to beat out x to the 2.9. Okay, because 24 is bigger than 2.9. And then after polynomial functions, logarithmic functions would work next, and then trigonometric functions. But for the most part, exponential and polynomial are going to be what you're looking for. One more thing we have to talk about is having to do with infinity inside of fractions, and there's actually an Edpuzzle that goes along with this. So I'm going to go ahead and we're just going to play through this, and then I'll talk through the answers. We won't go all the way to the end, but I'm going to play this.
To understand calculus, we first must reinforce the concepts that are fundamental to its foundation. I believe the key to understanding calculus lies in teaching these concepts. The algebra and complicated math that trips students up can be learned in time, but a student who never grasps the fundamental ideas of calculus can never succeed. So, let's take a step back from everything we know about math and try to learn calculus in a whole new way. So infinity is really cool because it allows us to talk about things that are either really big or really small. Infinity has this reputation of being known as the biggest number. Have you guys heard of that before?
Yes.
Yes.
It's not.
It's not. Yes, you're correct. If I asked you guys to count the numbers between 1 and 2, 1.1 is slightly bigger than 1, right? And it definitely is between 1 and 2. We all agree?
Yes.
So right now, we have one number between 1 and 2. 1.11 is also between 1 and 2, right? It's a little bit bigger than 1.1, right?
Yes.
So now we have two numbers that are definitely between 1 and 2. 1.111. This is also between 1 and 2. So if we keep adding ones, that's what this dot, 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 dot means over there. That means...
So the first thing that it wants us to kind of talk about is infinity is the greatest positive number, negative infinity is the greatest negative number. Is that a true or a false statement? And he kind of touched upon that, and so did the one student who shouted out in class so far, that infinity is not actually a number at all, right? Infinity is a concept, and so we would say actually false here.
That means we can just keep adding 1 on to the end of this number forever, and every single time we add 1 on, the number gets a little bit bigger, right? So it's a unique number. It's a different number that's between 1 and 2 every single time we do this. And if we keep counting these numbers, as in how many numbers are between 1 and 2, we'll never end. That is infinity. Infinity is a concept. And this is crucial to understanding not just infinity, but also for calculus. So, now with that, let's talk about 1 over infinity. If I have 1 over 2, we have this one pizza, we cut it in half, and this red right here is the amount of my one slice. We all agree?
Yes.
So now let's go to 1 over 3. We have this one pizza, and we divide it into 3 equal slices. This red slice is the amount of one slice. And now if we divide it into 4, what do we notice? It gets even smaller, right? So when we have 1 over 5, it's a little bit smaller. Okay? 1 over 6. 1 over 15. Let's look at 1 over 80.
Whoa!
What would happen if we go to 1 over infinity? The question is it equal to 0? So remember that infinity is not a number. So 1 over infinity doesn't represent anything. Remember, we had to have a number on the bottom of this thing, right? We have to divide it into a certain number of slices. And if we divide it by infinity, to me, that means nothing. But what does that mean about our pizza slice? Well, we said it's not equal to 0. But what we can say is that 1 over infinity goes to 0. When we increase that number on the bottom, our slice gets...
So what do we notice about the fraction 1 over n as n keeps increasing? So as he kept increasing the number on the bottom of the fraction, like 1/2 was half of a circle, 1/4 was a quarter of a circle, your slice kept getting smaller and smaller and smaller. And so what we can say about the fraction 1 over n as n keeps increasing is the fraction keeps decreasing or getting smaller, and it will approach 0. So as your bottom of the fraction gets infinitely large, we would say that the whole fraction gets infinitely small. Okay, and that's where we're actually going to stop the Edpuzzle video, and I want to go and do a couple of problems practicing these concepts. So I'll go ahead and zoom in here.